So in this video, I will mainly talk about the topics on harmonic oscillators. So basically everything in oscillatory motion can be based on its canonical model, like a spring with spring constant K is attached to a block with mass m, and the system experiences drag force proportional to the velocity of the block. And so the equation of the system can be written as x double dot plus 2 gamma x dot plus omega square x equals to 0, where we define 2 gamma to be b divided by m and omega is k divided by m, or b is the constant proportionality of the drag force. The differential equation can be easily solved by extracting the characteristic equation, which is x squared plus 2 gamma x plus omega squared equals to 0. And the solution of this quadratic equation will be the exponents of our exponential solution function. So we have x as a function of t is a e to the negative gamma plus omega t plus b e to the negative gamma minus omega t. And here we define omega square to be gamma square minus omega square. And here, omega is an important quantity, and the entire discussion on different cases of oscillator will be based on the sign of omega. And also note that the reason we have two undetermined coefficients a and b is because this is a second order differential equation, and we would have two linear independent solutions. So physically this means we need both the initial speed as well as the initial position to determine the motion of the object. And the first case is that omega squared is smaller than 0, so which means that omega is entirely an imaginary number. So we define omega to be I times omega twiddle, and so basically we're extracting the imaginary part of the big omega, which is a real number. Then we write the equation of motion to be e to the negative gamma t times a e to the I omega twiddle t plus b e to the minus I omega twiddle t. And in order to write this more compactly, we will use the trigonometric identities. If we say like a plus b is c times cosine phi, and a minus b is I times c times sine phi, and we will figure out that x as a function of t is actually e to the minus gamma t times c cosine omega twiddle t plus phi, and phi here is the phase angle. So this is pretty much everything we should talk about for the underdamping case, and there are a few remarks about the results. So first of all, omega is, as we will see, omega is smaller than 0 is the only case that we will have an oscillatory solution, and plus the oscillation is bounded by the envelope as a function of e minus omega t. So basically the amplitude is exponentially decaying, and also the frequency omega twiddle is less than the natural frequency of the oscillator. And the second case is when omega square is bigger than 0, which corresponds to the overdamping case. So omega would be a real number. Then if we go back to the general form of the solution, we would find the solution in this case is x as a function of t is a e to the minus gamma minus big omega t plus b e to the minus gamma plus big omega t. And since we do not have any trigonometric functions in this case, the solution is entirely decaying. There's no oscillatory stuff. And also note that most of the textbook contain illustrations showing that the solution is exponentially approaching the horizontal axis but not touching it. And yet, in fact, crossing the origin is entirely possible if the object has enough initial speed, and this can be observed in the following graphs. So what's indeed impossible is we cross the origin twice. In that case, we essentially have an oscillatory motion. And the last case is when omega is 0, and this is the critically damped case. In that case, we have one solution of the following form: x as function t is a e to the minus omega t. And since this is a second order differential equation, we definitely need to find another solution that is also linearly independent from this one. So we try with a solution of the following form: x of t is b times t times e to the negative omega t. And if we plug this back into the original differential equation, we're going to find out the terms, like all the terms cancel out. So x as a function of t is also a solution to the differential equation, and it is also linearly independent from a e to the minus omega t. So our guess is also a solution to the differential equation, and the general solution can be written in this form: x a function of t equals to e to the minus omega t times a plus b and t. And as usual, a and b are determined by the initial conditions. And so the critically damped case is the case for which the motion converges to zero in the quickest way.